Okay, about to start our next video. Of course, gotta have a little meme right here. What's a little math humor? So, the one video is out there with the start of the Taylor polynomials. Let's see if my new recording studio works better today. Let's see. Make a few minor adjustments. Okay, so we talked about Taylor polynomials in my first video for today. We're going to expand that discussion. I want to remind you that a Taylor polynomial can approximate functions that we don't know about. And we do know a lot about polynomials, or we should, but we have in our calculus careers used tangent lines to approximate functions. And we have also, because we are big bad BC students, used Euler's method to approximate functions. And so as I said in the first video about Taylor series, they are also used, but they're more accurate way to predict functions that we don't know about. So yesterday we talked about the sine curve and approximating sine, and we used a tangent line for one approximation, and then we did this work right here. Let me get this out. That was on the first video, which you probably just watched, and then we got this pattern for sine down here, and this we can use to mimic the sine function. And the higher the degree we go, clearly this could go to infinity, this degree, but that would take a minute. The higher degree we go, the more accurate our prediction of the actual sine curve is. And now remember, we predicted yesterday, or last video, sine of 0.2, because that was close to 0, the center that we were using. So that's important, that your prediction is only going to be as good as you are close to the center of what you're doing. So if you look, here's a picture of the sine curve and a tangent line at 0. That function at the center, the tangent line and sine are going to be exactly the same because it's the center of our sine approximation. And what we need to remember is that if a line works well, then a polynomial of higher degree is going to be even better as a prediction. So let's try this again, see what we can do here. In example 5, the next one, it should be write a Maclaurin polynomial. Do you remember the first video about Taylor series? I mentioned that Taylor and Maclaurin came up with these things. Maclaurin, though, if you have that, you know that the center is going to be 0 if it says Maclaurin polynomial. So we want degree 7 again, and we're going to predict the cosine function. So let's go over this pattern one more time. Here's how this is going to work. If we have f of x equals cosine, right, we're going to plug the center in here at 0. What's this function equal? Well, that's going to be a 1. And remember, this tells us our coefficients for our pattern. So let's keep going. We got to take the derivative, and the derivative of cosine is negative sine. We're going to plug the 0 in there. Of course, we get 0. And a second derivative, this is so much fun. Derivative of negative sine is going to be negative cosine. I can hear you all telling me this. And if we put a 0 in there, we get negative 1. Let's take a third one, guys. And now, isn't that going to be positive sine? Perfect. So when we plug a 0 into positive sine, we are going to get 0 out. And we have the first 4. Do you remember this could be a pattern? We saw that yesterday with our sine. So I bet we can figure out the pattern here, and we can stop taking our derivatives, because potentially we would need to do 7 of those, right? But we're going to go and jump into the pattern. And here's how this is going to work. So the first term is going to be a 1, and then plus 0 over x. over 1 factorial. Do you remember this happening? And then this would be x to the first, right? X minus 0, because our center is 0. We're thinking of x minus 0, so we're not going to write it like that. We're just going to write it as x. And then, so that's for the first, the second coefficient 0. The third one would be minus, and this is going to be a 1 in front of x squared over 2 factorial. Are you remembering this pattern? Plus then 0 times x cubed over 3 factorial. Beauty of these is this is going to be the pattern all the time. Now, can we predict the next one? If we took the derivative of sine again, wouldn't that be plus a 1 over 4 factorial x to the 4th? How far do we have to go? Well, we have to go till we have degree 7. So what's next? Aren't we going to have plus 0 over 5 factorial x to the 5th? I believe this one will be minus, and we will have 1 over 6 factorial x to the 6th. And what's our last one? Plus 0 over 7 factorial x to the 7th. Okay. So what's going to happen with our 7th degree term is that's going to be 0, isn't it? So we're just going to write this cosine out like so. Cosine x is approximately, we can predict it with a polynomial degree 7, which there isn't a 7th degree, and that's going to equal, let's get rid of all those zeros. We're going to let them go. 1 minus, this is going to be x squared over 2 factorial, 0, and then plus 1 over 4 factorial x to the 4th, and then minus 1 over 6 factorial x to the 6th. You get the idea. We could do this all day, but we're not going to. And so we also need an nth term. Aha. So here's our polynomial that we wrote out. I'm going to degree 6 because this one is a 0 term. I could figure out the 8th degree, but there you have it. So now if I'm going to write out my nth term, let's do this again. So x squared over 2 factorial. So 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. We're going to do our plus dot 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 plus. Now we got to think about how to do this nth term. It is one of our alternating series. Big tip off, we're going to need a -1 to the n. We'll see if we'll leave it to the n. And now notice all these exponents. Well, this is x to the 0, then x squared, x to the 4th. How could we do that? I believe we could do x to the 2n. And now isn't this going to be over the same factorial as our exponent? And then plus dot dot dot. And what can we start this one on? I believe this would be for all n greater than or equal to 0. Would that work? You guys check that out and think about it. So could I also write this in our summation notation? And we would do 0 to infinity. And it would be -1 to the n to, oh, no, my bad. X to the 2n over 2n factorial. So you can write it out either way. So if AP asked you for this, you can write it out here with your dot 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 and your plus and write it as the nth term here, or you can have it as using your summation notation. How cool is this? Well, yes, it is very cool. I can hear you all saying it's very, very cool. I would like us to take a look at, remember we did sine yesterday? We'll switch this. High technology going on here. So remember yesterday we had the sine one, and now we have the cosine one. Do you see patterns? Did you know sine was an odd function, and therefore these are odd degree terms, and cosine is an even function, and these are even degree terms? Wow, that's pretty exciting stuff. I hope I got all of that in there and you could see everything. And I'm having so much fun. I'm going to try another one of these. Here we go, guys. Again, a Maclaurin polynomial. That means our center is 0. So, of course, we would think of this as x minus 0 when we set up our pattern. We need degree n equals 4, and we're going to do e to the x. Well, this is an exciting one, I'd say. We're going to take, and we're going to put f of x, let's put a 0 in there. Oh, look, we get a 1. And then let's take the derivatives. Oh, this could be painful. What's the derivative of e to the x? Yes, I hear you. It's e to the x. And so we put a 0 in there and we get a 1. And this is starting to look a little bit redundant. Second derivative of e to the x continues to be e to the x. Put a 0 in there, we're going to continue to get a 1. Guys, I think I'm ready to write this polynomial. I don't know about you, but if we're going to take and write our polynomial out, we're going to have a 1. Won't we have 1 plus 1 over 1 factorial x to the first plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. What do we want? Fourth degree. Plus 1 over 4 factorial. There we go. Looks better. X to the fourth. Looky there. So e to the x is approximately, remember we need squiggles because we're not writing this to infinity, so squiggles. When I write it all out like this, I don't need to put squiggles. And I'm using a polynomial of fourth degree, and that equals, now I can put equals here, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. And there we go. We have our beautiful polynomial, fourth degree. I do believe this has asked us for an nth term. So if we write that out, we're going to have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth again over 4 factorial plus ... plus. Now for our nth term, doesn't alternate, no need for our -1, right? So what's going on here? This one's pretty simple, guys. Isn't this just x to the n over n factorial? Plus ... and we can start this one for all n greater than or equal to 0. Look at there. We like E. E is our friend. He's pretty easy. So I hope you enjoyed that. Hold on for a little bit more examples coming your way.